Hi, everyone. We are back for our last P-Set for this semester. So P-Set 8 solutions. So let's go ahead and get started and let's maximize. So we're looking at some results from electrochemical measurements. Fill in the table. What are the standard conditions? Temperature equals 298 K. Pressure equals 1 atm. And then we're in a 1 molar concentration of our own ions. Let's see, what is standard conditions? List a little quantitatively. For the standard conditions, what material will corrode? So we need to fill out this. So what we're going to have to do, we'll bring up Mathematica. We'll bring up our little table of potentials. And what are our materials here? Let's try to remember. Actually, we could try to drag it down just a little bit here. Perfect. Okay, so CO is equal to, let's look at our table, minus 0.277. Fe is equal to minus 0.440. Mg is equal to minus 2.363. Nickel is equal to minus 0.250. Zinc is equal to minus 0.763. Zinc, lead is equal to minus 0.126. And let's see, 0.26. Platinum is equal to 1.2. And SN, tin is equal to minus 0.136. Perfect. All right, so now we can do, again, we always do, again, our E naught is the positive terminal minus the negative terminal. So let's go ahead and do CO minus Fe, Mg minus Ni, Zn minus Pb. Oops, Pb. Zn minus Pb, Pt minus Pb, and then Sn minus Co. And we can kind of double check that this makes sense. So again, if electrons are flowing from negative to positive terminal, that means that we have a positive voltage. We know, for example, that Pt is going to be super electronegative, so the electrons are going to flow there. So that makes sense. We should expect a negative E naught for Mg minus Ni, and we've got that. So there we go. So what's going to corrode here? So iron will corrode because we're losing electrons there. Mg will corrode. Zinc will corrode, Pb will corrode, and then here Co will corrode. So there we go. For the non-standard conditions, what materials will corrode? So here, for the non-standard conditions, it would be this, it would be this, it would be this, it'd be this, and it'd be this. Based again on, where those electrons are flowing in the terminal there. So excellent. Turns out non-standard conditions occur at 700 K, so we're going to have to use our E minus E naught equals minus, I always forget this. Not necessarily forget, but we'll go ahead. We'll use this as an opportunity to look at our, again, textbook. So we have a textbook. Ooh, not RStudio. So we have a textbook in this course. You can look at LibreText. It is a free textbook for you to utilize. Let's just wait while this loads up. Take a sip of my coffee. And we are going to go to our textbook and we can look at corrosion. We could also see our YouTube videos that, again, they're linked here where you can see those. We're going to use, we're going to use lecture 7 or chapter 7. And then we're going to go here and we are going to look at our Nernst equation. And our Nernst equation says minus RT over NF. So we can go ahead and set up our function and say, first R is equal to 8.314. And then Faraday's constant is equal to 96485. And N, we're just going to assume it's always 2 for this particular problem. So let's go back to our OneNote. So it turns out that these things occur here. What is the ratio of cathode versus anode ions for the non-standard PT and PB measurements. What's the ratio for standard conditions? Well, we know the ratio because, again, it's minus RT over NF, and then it's natural log of, and whenever we have the reaction, it's, so for example, if we look at PT and PB, we know electrons are flowing from here to here. So if we look at the half cell reaction here, it's PT in the 2 plus 2E minus goes to platinum. Here, PB is our reactant, and it goes to, let me erase that. Let me see. PB goes to PB 2 plus 2E minus. So our full cell reaction will be something that looks like this. And the standard conditions, so PT 2 plus PB goes to PB 2 plus platinum. So our concentration of products, which is going to be concentration of PB 2 plus, over our basically reactants, which is PT 2 plus. And then again, in this scenario, this is the true cathode. This is the true anode material. So that's asking concentration of cathode over anode. So we're actually looking for the inverse of this. So that's the trick to this problem. So whatever we solve for in this X, we want to take 1 over X to get that ratio. So let's go ahead and do just that. So we don't need this anymore. So we're told those things. We're also told that the temperature occurs at 700, and we're doing PT and PN. So we can just say, and then we are also given, what is the E for PT-PB? Yeah, so the E PT-PB is equal to minus 1.82, and then our E naught PT-PB is equal to 1.326, as we just see right there. So we're going to solve E PT PB minus E naught PT set equal to minus R times T divided by N F. And then I'm just always, people are going to probably be annoyed that I always do this, times natural log of X. And we can solve for X, and then we can just flip that ratio. So 1 divided by that will give us our answer for that ratio. So there we go. Fantastic. I want to create a sacrificial anode for the system of CD and AU. What material would work? So if we look at so we need to protect CD because CD is going to be the one that corrodes here. So basically we want anything that's below CD, increasingly anodic. So because we know AU is higher, so CD is going to corrode. So iron, chromium, zinc, aluminum, magnesium, potassium, and sodium, they all can work. Would Al work? Let's take a look back. Al, where's CD? Al. First of all, we don't even see that. Al would work. Yes, indeed. So there you go. And that is it. That is your problem set 8. So thanks, and see you in the next video and the next semester or in another class. Thanks. Bye.